Hi class, this is Professor Mahan. This is a lecture on 5.4, the net change theorem. So after we've learned about the antiderivative, finding the antiderivative using the fundamental theorem of calculus, here are one of the applications of doing the antiderivative. So here, the integral of a rate of change is this net change right here. That's the fundamental theorem of calculus, in other words. So how this is applied is that there are two situations. I'm sorry. So in terms of physics, if you remember the particle that we were talking about in other chapters, there's displacement and there's distance. Displacement is where a particle has traveled from one point to the next point, right? So how much has it displaced? So if I have a particle that's starting here, it could have displaced and it went from here to here, then it really from here to here, it only displaced this much, right? So maybe I should just draw a picture. So here's my particle. So say the particle moved here, then it went back, and then it moved here. So what's the displacement? Well, the displacement is just really from here to here. The displacement is where it ended off compared to where it first started. What was the displacement? Now the distance is the distance that it traveled. So the distance that this particle in this example traveled is it traveled here. So here's the distance, plus it traveling here. I'm sorry, here, right? Or all this distance. So the distance it traveled, it would account into it going backwards and then moving forward. So that's called distance. So when you're thinking of distance, we want to take the absolute value of velocity, because remember the antiderivative of velocity is the position. So maybe I should write this down here, reminder, that the antiderivative of velocity is the distance, right? So the distance that something traveled. Or if you think the derivative of the distance of the position will give you the velocity. So if you're given the velocity and you want to find the displacement and the distance something traveled, you take the antiderivative. The displacement, again, is how much it moved going from beginning to end. And if it went backwards, you don't account that. So just from here to here. The distance is the total distance. So if it went backwards, you consider that a number. So even though it went backwards and it's a negative number, you want to take the absolute value of that to make it positive, and then you add it to the distance it went forward to give you the total distance. And that's why distance has absolute value, because when it's moving backwards, you still account for that. So here's an example, which this is a very short lecture. We only have one example here. Here's the velocity of the particle, and here's the time that it traveled. Find the displacement. So the displacement here, this is the easier part. Displacement is t1 to t2, so the times from 0 to 5. Those are the endpoints of our integral of the velocity. Velocity is 3t minus 8, and then take the antiderivative of that. So this is the regular antiderivative problem. So I'm going to add 1 to the exponent and divide by the new exponent. So I have 3 divided by 2. Minus, here's 8. The antiderivative of 8 is just 8t. Using the fundamental theorem of calculus, I go from 0 to 5. I plug the 5 in. So here I'm going to plug the 5 in, and then minus, I plug the 0 in. So here, I'm going to plug f of 5 minus f of 0. So when I plug 5 in here, I get 3/2. 5 squared minus 8 times 5. Minus, you plug a 0 in here, you get 8 times 0, right? And I'll let you figure out the answer for that. It's a numerical number. It's going to be positive, right? So here, find the distance. So the distance traveled here is taking into account if this particle had gone backwards, you want to make it a positive. So we want the absolute value of the antiderivative of the velocity. So here I have from 0 to 5, and I want to take the absolute value of 3t minus 8. Well, this is a tricky part, so careful. This is harder than finding the displacement, because you only want to find out, you want to find the absolute value of this. So the absolute value of 3t minus 8, if I drew a picture of 3t minus 8, this is going to give me a positive slope with the intercept of -8. It's going to go like this. So this is 3t minus 8. So notice from the time, so we're only looking from time 0 to 5. This is t. Notice from some time here to this time here, it's going to be positive, but down here it's going to be negative. So what is that point here in which it touches the x-axis? Where does it cross the x-axis? So what you do is you set 3t minus 8 equal to 0. So 3t is equal to 8, so t is 8/5. So notice from 0 to 8/5, I'm going to have a negative displacement. From 8/5 to 5, I'm going to have a positive. So from 0 to 8/5, I'm going to need to change this 3t minus. So let me just show you what I'm going to do. So here I'm going to take 0 to 8/5. 3t minus 8, I'm going to take the absolute value of that. Well, the absolute value of 3t minus 8, it's going to be negative here. So to make it positive, I need to stick another negative here. So negative 3t minus 8 dt. So I have that. Plus, I'm going to take the antiderivative from 8/5 to 5. And this is going to be positive, so I'll just leave the integral the same. So here, this accounts for the area underneath the curve when it's negative here. I'm going to make it positive by flipping this to make this a negative sign. And then this is a positive area, so I just leave it as is. Okay, and then from then on, I could use the antiderivative to find this and then solve for my answer. So I just wanted to set up the problem so you can see how it works. Let me know if you have any questions.